So hi everyone, so now we are going to look at the problem 2 of the tutorial 8. So for the problem 2, we are going to look at a model that is a 3-element model with one spring and one dashpot in series here and a spring in parallel to this system. So we are applying a constant stress, and here we have the modulus 1 for the spring 1, the modulus 2 for the spring 2, and the viscosity of the dashpot. So for this system we know that E1 equal E2 equal 1 gigapascal. We know that the viscosity of the dashpot is equal to 100 gigapascal second, and we are asked to calculate the stress. So we are asked to calculate the stress at 60 seconds. If knowing that at T0 we are going to apply an instantaneous strain of 1%, and that is going to be kept for from this stress of 1% will be kept from t equal 0 second to t equal 100 second. Right. So what we know here that when you just look at these assumptions is that we have a system where we are going to have a strain that is constant, and so we are going to look at how the stress evolves. All right. So this kind of system is the type of test for stress relaxation. All right. So we are looking at the stress relaxation system. So I hope that makes sense to everyone. You should now know that when you have a system, when you apply a constant stress and you look at the strain, you have a creep test. When you have a system where you apply a constant strain and you look at the stress, you have a stress relaxation test. All right, so that should be clear by now for everyone. So when you look at this system, you notice that it's exactly the same system as last week, that for which we derive a stress-strain relationship. Okay, so you can go back to the tutorial 7 problem, the tutorial 7, to look at how this was derived in details. Now, for this tutorial, for this problem, we are going to just use the expression that was derived at the end of the problem last week. So we obtain, after the solving, we obtain a system with that look like 1 plus modulus E1 divided by E2 times the derivative of the strain over time plus up okay. So this is the expression that we had for this 3-element model. So you notice that in this expression there is no assumption made yet. Like this is a general model. It can be valid for either creep or stress relaxation test or anything. So so we can just simplify it, because now we know that in this system we'll be working in a stress relaxation. So if we work in a stress relaxation, it means that the derivative of the strain over time is equal to 0, right? Because the strain is constant, 1%, at least from 0 second to 100 second. So then it means that we can rewrite this as okay. So this means that we can. So this means that we can just express this. So as so I'm just going to multiply everything by E2 to obtain a form where the derivative is not multiplied by anything. So this is a form that is, so this is just a way to get to a form that is easier to derive. All right. So for this type of form, we know that we can use the following expression. So this is y prime plus ay equal b. Okay, so we have an expression roughly like that. So for this kind of expression, we can use, we can integrate it, we can solve it with using this general expression. So for this part, you will have to look back a bit at how to solve differential equations. Okay. Oh, sorry. So we have the general expression that looks like that. So the y would stand for the stress, right? And the b would stand for this element. The a would stand for this, right? So this is just a general expression that we can use to solve this kind of differential equation. So now the only thing to do is just to solve this. So we are going to write that the stress is equal to, over time, is equal to the exponential of all right, and we are going to do E1, E2 divided by the viscosity times the strain, right? Apologies for this, is actually y prime, the y prime plus ay equal b, right? So the whole b term is equal to this. And okay, so let's continue, and we are going to write this as in the expression. All right, so now we can just solve the individual components, right? So here, this is going to make it equal to E2 divided by the viscosity times the time, right? Because we just integrate dt. Now, for this one, we are going to be able to take out this term out of the integral because it's a constant. All right, so now we have a system like that. So for which you would, so we can also solve this term the same way as we did for this term, right? So we would just write this as E2 okay, so we're getting quite close now. The only thing that we have left is to solve this integral. So we know that the integral of e, the exponential ax is equal to 1 over a exponential ax, right? So this is basically, to solve this, we would just rewrite this as all right, so we'll have an expression like that. So for when you see with this term, we see that we can cancel the viscosity and the modulus here. So if I continue solving this, I do need to have a new sheet of paper. But continuing to solve this means that we get to the final form of E2 divided by the viscosity times the time dt plus c. All right. So this is something that you should be able to do without too much problems, right? Something that you would have done through your undergraduate studies. So having this form, now the last thing to do is to calculate the constant c. Okay. So we can just start by listing what do we know. So we know that at time equals 0 second, we have epsilon 0 that is equal to 0.01. So the 1%. This is the condition that was set in the problem. We also know that at t equals 0, we have the stress applied on 1, which is the Maxwell component, which is the spring, sorry, plus the stress applied on the Maxwell component is equal to the total stress, right? So what we know as well is that at t equals 0, the dashpot does not respond, right? Since the dashpot is a function of time, if you are looking at the instantaneous response at t equals 0, the dashpot component is eliminated. So it means that we can just write this at t equals 0 second as the stress being the sum of the springs. So you would write E1 epsilon 1 plus E2 epsilon 2. Okay. So we have this form for sigma dot sigma 0 second. So now that we see that from the assumption that we made based on the model that we use, we can look at the expression as well. And if we look at this expression, if you put t equals 0, you will obtain a form that is of sigma 0 equal to E1 epsilon plus c, right? Because this is equal to 1, this is equal to 1. So we will just have everything cancelling, but we just have all those two exponential terms disappearing. So we obtain E1 epsilon plus c. Okay, apologies for this, ignores dt here. This is just a mistake. So we just have this form with this one cancelling, E1 epsilon plus c. So now, this means that if you put those two expressions together, we know that sigma 0 is equal to E1 epsilon 1 plus E2 epsilon 2. We know that epsilon 1 is equal to epsilon 2, right? This is the assumption we can make from the model. So we also know that sigma 0 is equal to E1 epsilon plus c. So we can say that c equal to E2 epsilon 2, which is equal to E2 epsilon. So we have solved our system. We know now that the constant is equal to E2 times the strain. So we are getting close to getting our final result. So we know that C is equal to 0.01 times E2. So looking at our model, we can now write it as all right. So if you just cancel the terms, like because this and this would be equal, would be E0, right? So would be equal to 1. So we would obtain a relationship, a final form of E1 epsilon plus E2 epsilon times the exponential of minus E2 divided by the viscosity times the time. So that's the final expression that we would have. So now, if we solve this, after 60 seconds, we would obtain E1 times 0.01 plus E2 times 0.01 times the exponential of minus E2 times 60. So if you plug in all the values, you will end up with 1.55. So this is how we solve this problem. The stress after 60 seconds for this system would be of 1.55 times 10 power 7 Pascal. So this wraps the tutorial 8. So essentially, if you look at what we have done today in the problem 1 and in the problem 2. So in the problem 1, we looked at, the trick was to be able to identify that the equation that we had for the stress relaxation described a specific model, which is a Maxwell model, and use this information to derive the creep component. In the second problem, on the other hand, the objective was just to drive through to remind you on how to solve a differential equation which has the form of y prime plus ay equal b, right? So because we already learned how to express stress and strain for this kind of model, today was more on how do we solve it and how do we calculate the constant for this kind of system, what type of assumption we made to be able to get the constant and obtain the final stress value. So I hope that is clear, and if you have any questions, do not hesitate to contact me. Have a good day and take care, everyone.